Hi guys, I am discussing our complex analysis unit 1 in which up to the last lecture I discussed what is analytic function, what is harmonic function, and then on the last lecture I started complex integral. I just started in the last lecture in which I discussed some theorems. First theorem I discussed Cauchy's integral theorem. Only a statement of this theorem is part of your syllabus. Proof is the beyond your syllabus, out of your curriculum, and in which I told you if we take a closed curve C and a function fz is analytic, then simply integral along C of fz is 0. This is the first theorem, Cauchy's integral theorem. And for multiply connected region, if we have multiply connected region like that, if we have two concentric circle and we take this region, and this is circle C1, this is circle C2, then this theorem will be reduced into this form. I have already told on the last lecture, this one. And then I discussed its converse, that is the Moraz theorem. Converse means if fz is continuous function and this integral is equal to 0, then fz is analytic. And also I took an example based on Cauchy's integral theorem because if function is analytic and there is a huge function, so there is no need of calculation. Only you check whether function is analytic in the given closed region or not. If function is analytic in closed region, then you can directly its integral value is equal to 0. And after that, I just stated Cauchy's integral formula. Cauchy's integral formula. I just stated on the last lecture Cauchy's integral formula, in which I discussed, I stated this: if fz is analytic on C and within C, and z equal to A is a point inside C, then f of A is equal to 1 upon 2 pi integral C fz upon z minus A dz. This is Cauchy's integral formula, which I stated on the last lecture. If function is analytic in a region, if this is a region C and point A is a point inside C and function is analytic, then you can find the value of function at point A in form of this integral. This is actually Cauchy's integral formula, and its proof is also part of your syllabus. So from this lecture, from today, I will start from here. First, I will prove this Cauchy integral formula, and also we can find the value of derivative by this formula of the function at point A of various order. So first, I will prove this. For proving this, let us consider a function phi of z as fz upon z minus A. Then you see that here phi z is analytic except at point z equal to A, because fz is analytic, it is given in the statement of Cauchy integral formula. So phi z is also analytic except z equal to A. And let us consider a small circle C1 with center Z equal to A and radius small r. That means C1 means mod Z minus A equal to small r, where r is very small. If we take this circle, means we are taking this as a circle C1. Then we can form a region between these two curves C and C1. Then R is a region between C and C1, and now phi z is analytic in R, right? Because it is not analytic. Now in this region, this is a almost a ring-shaped region bounded by these two curves C and circle C1, in which function is analytic, and so by Cauchy's integral theorem for multiple connected region, we have integral C of phi z is equal to integral phi z along C1 by this theorem. Means if you substitute the value of phi z, we consider phi z is fz upon z minus a dz, C1 fz upon z minus a dz, this one. Now we can now calculate value of this integral, by which we can prove the given statement. How we can calculate this? Here in numerator add fa, and for balancing subtract fa upon z minus a dz. This is simple. Fa is subtracting, then fa is adding, and if you separate this, we get two integrals, fz minus fa upon z minus a dz plus integral over c1 fa upon z minus a dz. Take this equation number 1. Now on the right hand side we have two integrals around c1, and c1 is a circle, as you assume that this is a circle with center point A and radius small r, on which we can calculate, because C1 is z minus a equal to r. If we put this into complex form, then we can z minus a equal to r e to power I theta, and by this, by substitution here dz is a constant, r I e I theta d theta, and limit, because it is a circle, limit theta from 0 to 2 pi. And so we have first integral c1 fz minus fa upon z minus a. Now you can calculate on c1 value of this integral firstly. What is the value? This is integral 0 to 2 pi. Fz means, put the value of z from here, a plus r ei theta minus fa upon z minus a is r ei theta, dz is r I ei theta d theta. From here r is cancelled out, ei theta is cancelled out, and this is 0 if r tending to 0, because C1 is a small circle, so r is always approaching to 0. If we take this limit, then this integral is 0. This is the first part of the right hand side. Now similarly you can calculate second integral of right hand side of equation 1. Now integral c1 f of a z minus a dz. Again For C1, this is integral 0 to pi. Fa is constant value. Z minus A is given by this circle R ei theta. Dz is R I ei theta d theta. This is R is again cancelled out. Ei theta is cancelled out. I is constant. And Fa is constant. We get 1. Integral 1 is theta. Limit 2 pi and 0. Right? And this is 2 pi I into FAR. This is the value of second integral on the right hand side of the equation 1. And so substitute these values in equation 1. So therefore, from equation 1, we get integral C fz upon z minus a dz. This is equal to 0 and this is equal to 2 pi I fa. And from here, we get finally value of fa is 1 upon 2 pi I integral C fz z minus a. This is your statement of the Cauchy's integral formula, and that is the proof of Cauchy's integral formula. Right? If function is analytic and z equal to a is a point inside a closed curve C, then value of that function at point A can be expressed in form of such integral. This is the proof of Cauchy's integral theorem. That is the first theorem which I stated on last lecture and proved today. Now, second, based on this theorem, there is another, that is Cauchy's integral formula for derivative of function. Cauchy's integral formula for derivative of function. This is also, you can say, an extension of Cauchy's integral formula. What is the statement? Same statement. If fz is analytic inside a closed curve C, and z equal to a is any point inside C, then f dash a is 1 upon 2 pi I integral C f of z upon z minus a square dz. This is the statement of the Cauchy's integral formula for a derivative of a function. You see that here f dash a means first derivative of function at point A. This is equal to, again, in terms of a definite integral, a complex integral. That is 1 upon 2 pi I integral C fz upon z minus a whole square dz. Again, first we see how you prove this statement, and also it can be generalized up to the nth derivative in similar manner. First, we see the proof of this formula. Again, it will be proved by the using of Cauchy's integral formula. By Cauchy's integral formula, we know that f of a 1 upon 2 pi I integral C fz upon z minus a dz. This is the statement of Cauchy's integral formula, and it will be applicable here because fz is analytic and C is a closed curve and point A is lying inside C. These are three conditions for Cauchy's integral formula. First, function fz analytic, C is a closed curve, and z equal to a is a point lying inside C. All the conditions are defined, so we can this. And now simply number of methods to prove this, but very simple method here I am using. Differentiating partially with respect to a. Take a as a parameter and differentiate this. In the left hand side, we get f dash a 1 upon 2 pi, and by in the sign of integration, if we integrate partially with respect to a, fz is out of this differentiation, and partial derivative with respect to a of 1 upon z minus a dz is again outside. This is the very simple method to prove this result. And here, this is 1 upon 2 pi I integral ci f of z, integration of 1 upon t means z minus a square, and this is with respect to a minus a dz minus us plus. Finally, we get f dash a is 1 upon 2 pi I integral c fz upon z minus a square dz. This is your formula for the derivative of analytic function. Alright? This is the first derivative. Similarly, you can obtain second derivative. Second derivative is 2 upon 2 pi I integral c fa upon z minus a whole cube. And in similar way, you can obtain, means you differentiate again. So you can obtain third derivative, that is factorial 3 2 pi I integral c fz upon z minus a power 4 dz, and so on. In general, in similar manner, you can obtain any derivative, that is the n fn of a factorial n upon 2 pi I integral c fz upon z minus a power n plus 1 dz. This is the main formula. This is the formula for any derivative of any analytic function by Cauchy's integral formula. And by this formula, you can obtain, you can find order, a derivative of any order if function is analytic by using Cauchy formula. This is the second formula. Now, before going to other theorems, I will discuss some example using Cauchy integral formula, how you can use this to solve the differential equation. If we have to numerical sum and you solve this by using Cauchy's integral formula, then what is the process and what is the application of Cauchy's integral formula as well as Cauchy's integral formula for the derivative of analytic function. So first, here I am taking a numerical example, that is example use Cauchy's integral formula to evaluate integral c z upon z square minus 3z plus 2z, where c is the circle mod z minus 2 equal to half, right? If we take this numerical sum, then you can understand what is the application of Cauchy's integral formula and how you use Cauchy's integral formula to evaluate such type of complex integrals. Take solution. Here fz is this, z upon z square minus 3z plus 2. And circle is this. Circle means if you draw on z plane, center is 2 and radius is this. This is center, radius this, and this is c. This is c. Now here first of all we have to check if fz is analytic inside c or not. And for that, here we have to find, there are two things which just in detail I will discuss in the next chapter, but because there are some application of such topics in this calculation, so thus just this, there is a term always, poles. Poles means points at which fz is not analytic. Means this is another name of singularity. I have already told you in the introduction of the lecture when I discussed about the analytic function. Then I told you a point at which function is not analytic is called similar point, or that is the similarity of function. And pole is a type of similarity, is another name of the similarity. Pole means if we have fz is tending to infinity at finally z equal to a. So actually this is a pole. And this is a two type. One is simple pole. Simple pole means the function is linear. And another is pole of various order. If not linear, then various order. So first we have to calculate what are the poles of this function. Here you see that fz tending to infinity at z square minus 3z plus 2 equal to 0. Factorize this, then z minus 1 and z minus 2 is 0. These are two factors, so z equal to 1, z equal to 2 are simple poles, right? These are the simple poles, right? And these are 2 points at which fz is not analytic. Now you have to see that, you have to check that whether these poles lie inside your region, your curve, your circle C. So 2 is extremely here because 2 is the center of circle, and 1 because half is this, so you can see that this is half. So this is almost 3 by 2. So 1 is not lying in this side. So only z equal to 2 is lying inside C, right? And at which function is not analytic. And then by using Cauchy integral formula, we can say if by Cauchy's integral formula, you know that fa equal to 1 upon 2 pi I integral C fz upon z minus a dz. If you simplify this, because we have to find the value of integral, so from here we have integral is this, and value is this 2 pi I into fa. If you compare this by given integral, because given integral is this, so and fz must be analytic, so fz we can this we have take fz is this, means z minus 1 and z minus 2 after factorization. So here we have to take in fz, therefore we have to take in fz equal to z upon z minus 1, because z11 is lying outside the C and 2 is a point inside C. So by Cauchy's integral formula, we have integral z upon z square minus 3z plus 2 dz equal to, this is 2 pi I into fa. Fa means f2, because a equal to here, fz equal to this, and a equal to 2. Now calculate the value of this 2 pi I. F2 means 2 upon 2 minus 1, that is 4 I. This is the final answer of this given integral. So by this method, by this process, we can use Cauchy's integral formula to evaluate any complex integral. Means here we have to see 3 things. One thing, C is closed or not. Second thing, given function is analytic inside C. Third thing, what is the point which is lying inside C, and at that point you have to calculate the value by the Cauchy's integral formula, right? This was the numerical example of Cauchy's integral formula. Now we come to our next topic, that is another theorem, that is Cauchy's inequality. This is Cauchy's inequality. This is the next topic. This is also a form of lemma, a theorem. Cauchy's inequality, what is the statement? If fz is an analytic function inside a circle C, z minus a equal to r, and fz is bounded. That means mod of fz is less than or equal to m on C, where m is, you know, that a positive constant. Bounded means here we are defining a boundary of a function, right? This, if this, then fna mod is less than or equal to factorial n m upon r to power n. This is the statement. If function is analytic in a given circle with center A and radius capital R, and function is bounded on C, then the absolute value of nth derivative of function at point A is always less than or equal to factorial n into m upon r to power n. Proof is very simple. By derivative of analytic function of Cauchy integral formula, directly you can prove that. We know that by Cauchy's integral formula, just I prove that nth derivative of this is factorial n upon 2 pi I integral c fz upon z minus a to power n plus 1 dz. This is just I prove this in the statement of Cauchy integral formula. So we can prove by this formula easily this inequality as, because on C we have mod z mod a equal to r, open this, then z equal to a equal to r e I theta, and you know that here dz equal to r I e I theta d theta, and because C is a circle, so around the circle limit is theta from 0 to 2 pi, and also on C mod fz is less than or equal to m. So first of take, if we take absolute value on both sides, factorial n upon 2 pi I integral c fz upon z minus a to power n plus 1 dz and mod. You know that when we take the mod inside the integral, then this equality becomes inequality, less than or equal. That is factorial n 2 pi mod I is 1, integral 0 to 2 pi. This is mod fz, this is mod z minus a n plus 1, this is mod dz. Because you know that mod I equal to 1, right? And now calculate this and you will get your required result. Simply put the value of mod n, mod z, mod fz, that is m, this is r to power n plus 1. Mod dz means or is 1, so r and d theta, because mod e I theta is also equal to 1, because you know that e power I theta equal to cos theta plus I sin theta. If you take the mod, then under root cos square theta plus sin square theta, and you know that sin square theta plus cos theta is 1. So r 1 power is cancelled out, and this is factorial n 2 pi, take m outside, r to power n outside, integral of 1 is theta, 2 pi and 0, that is 2 pi is cancelled out. Finally, we get nth derivative of fa is less than or equal to m factorial n upon r to power n. That is your required result. That is the proof of Cauchy's inequality. In this chapter, as I told you, only some theoretical part of the complex analysis, complex integral. So we discussed complex Cauchy's integral theorem, Cauchy's integral formula, Cauchy's derivative of analytic function, converse of Cauchy's theorem, that is Morat's theorem. And in this lecture, I discussed Cauchy's inequality. And now in coming lecture, only two theorems are left according to your syllabus. That is the Liolius theorem and fundamental theorem of algebra. In next lecture, I will discuss these two, and this is your first chapter, first module, complex analysis 1. Okay, thank you.